the context of our lecture tonight, I'll be talking about knowledge representation and reasoning, and primarily intelligent agents. I'm going to skip a lot of the boilerplate stuff about the module. I will prepare kind of a 10-minute overview video in terms of kind of learning outcomes, assignments, topics we'll cover, recommended reading, etc. But we only have 2 hours, and I delivered this lecture this morning as well to the full-time MSc in AI, and it took 2.5 hours, as I don't have that time with ye, because you have a lecture after me, don't you? Do you?
We do, yeah.
Yeah. So we're under time pressure in that sense. Okay. Is that okay with you? So I'll get cracking. Okay. So what we're talking about is intelligent agents, and really, from that perspective, we have to kind of define what we mean by that. But first off, we want to talk about acting rationally. Okay. So what is rational behavior? It's doing the right thing, and again, it's doing the right thing given the available information. So the right thing here will be defined as that which is expected to maximize goal achievement given the available information. So this doesn't necessarily involve intelligent thought or thinking. So again, you can take examples of your blinking reflex. So you know what that. When you blink to stop something getting into your eye, that's an example. If somebody throws a rock at your head and you duck, that would also be an example. So when we think, well, thinking should be in the service of rational actions. So we take a definition by Aristotle: every art and every inquiry, and similarly every action pursuit, is thought to aim at some good. Okay, so in the context of rational agents, what do we mean by that? So an agent is an entity that perceives and acts. So again, this course is about designing rational agents, and we have to think about that in kind of from an abstract perspective, whereby an agent is a function that maps percept histories to actions. And again, we have a function, percept histories, mapping to an actual particular function. Now I have a raised hand, and I have to figure out how I answer the raised hand, because I'm getting rusty. So Saeed is saying, what about the wrong thing? It is also an action. Okay. From the perspective of your perception of the world, given the percepts you perceive, if you act and it means that maximizes your performance or to achieve your goal, then that's not the wrong thing. Now, if you're talking about things in your environment or your world you can perceive, then you would still consider that agent to be rational, or it to be a rational act, because you're acting on the basis of the information you have available to yourself. Okay, does that clear that up? So for any given class of environmental tasks, we seek the agent or class of agents with the best performance. Now, like, we will be looking at a number of limitations around designing these agents, and why we can pick simpler approaches are more appropriate in some places, and while more, well, simple is kind of a, yeah, simple is like, you know, simple is a good word for it, because simple solutions can be powerful solutions, and if used in the right context. But there are obviously more kind of advanced solutions for particular tasks, which we'll also explore. The main thing that will actually force us to pick one or the other is computational limitations, because typically these make our perfect rationality unachievable. And again, it's kind of self-evident if you consider that as the number of percepts increases, which you can kind of think about in terms of improving the accuracy of the model of the world around us, that the computational computation associated with that becomes more difficult. So what we're looking to do is design the best program for a given machine resources in terms of achieving our rational agent. Okay. Okay, in the context of AI and rational agents, what can be done at present? Okay, so these are listed things now. So I mean, okay, if we were to say, play a decent game of table tennis, can a rational agent be created to do that? What would you think? Yes or no?
Yeah.
Yes.
Absolutely. Again, you'll have all seen kind of advances in robotics, where you just have a robot automated hand that holds a paddle and a camera that's perceiving the ball as it's moving, calculating the trajectory, and then you calculate the trajectory at which to hit the ball to return to the other side of the tennis. So that's a yes. Driving safely along a curving mountain road, that also will be a yes. Okay, we've seen great advances in the last number of years in terms of autonomous vehicles. But now if I was to say something like driving safely along Telegraph Avenue, what would you think about that? Or what would be the distinction between that and the prior example?
Might be more people around, so it could be dangerous.
Yeah, that'd be a physical limitation of the world, okay. But the main challenge there is Telegraph Avenue, you know? I mean, now our agent not only requires the capacity to perceive its environment in terms of the type of road it's driving around, the type of terrain, the physical characteristics, people, traffic, etc. It also means an understanding of where in the world this is, okay? So that increases the complexity of that agent. So it's not there yet, okay? In terms of buying a week's worth of groceries on the web, yeah, that's pretty easy. Buying a week's worth of groceries at Berkeley Bowl, again, same limitation as before. Decent game of bridge, yes, that's perfectly fine. Discover and prove a new mathematical theorem. What do you think?
No.
Anyone else?
It has been done, but it's limited.
No, yeah, but I mean, no, I mean, they have made significant advances in this. And again, in many senses, it's kind of a more achievable problem because mathematics has a solid structure to it. You know, once you understand the rules, the concepts behind maths, then you can automate a lot of that intelligence. So I've seen papers, for instance, that in both mathematics and in bioinformatics, say for drug discovery, where they're parsing the abstracts of these papers, of thousands of scientific papers, and then they're trying to see can they align the contributions to these papers to make incremental improvements in the actual theorem being proposed or in the makeup of a drug. Okay, and because they've shown that they can kind of get ahead of the curve in approximately 6 months ahead of the scientific community. You know, there's quite often, you know, a mathematician might release a paper introducing a new concept, and then you'd have a series of papers published on the application of that theorem in different domains or for different problems. So they can automate that. So in that sense, they are both discovering and proving new theorems. Okay, so design and execute a research program, molecular biology. Yeah, I mentioned drug discovery. Writing an intentionally funny story. What do you think about that one?
That's a bit harder.
Yeah, it's a very hard one. Okay, so like, while the semantics of language would have a good structure from which you could work with, we don't really have the interpretation of what we consider funny. You know, I mean, if you take the basic example of a pun, you know, so it's like we can either play on words or the sounding of it. You know, we would get that intuitively, but a machine is almost, you know, not impossible, but it needs a representation that enables that relationship and representation to be surfaced before it would be capable of deriving that. Now, there have been great advances in NLP in the last number of years, which are getting us closer. So So I've seen some papers that they look at, rather than using a human-based structure for language, they use a machine-designed one. So they don't even actually, they do it, this just feeds so much data that it comes up with its own internal representation of what language is. And that has seen great benefits in terms of, say, translation of languages. But there hasn't been significant study or invested time in terms of generating what we'd consider funny. So that's a no for now. Give competent legal advice in a specialized area of law. What do you think?
Yeah.
Yeah, possible.
Yeah, 100%. So like, this is kind of a big area because particularly with the likes of, say, case law, where you have to review prior precedents that arise from previous cases being seen by judges. You can basically harvest the data, try and build a structure out of it, and then try and do searches based on that to provide you the information you need. Translate spoken English into spoken Swedish in real time. Yeah.
Yes.
That's quite a, you know, I mean, we're on top of that at the moment. If any of you have seen kind of the, I don't know, like Google Translate, Apple have their own version where like you can speak in one language and it will translate it into AirPods, what are they called? I can't remember the name of them. So yeah, that one's, you know, it might be perfect, but it's getting there. Converse successfully with another person for an hour.
That's really the Turing test, isn't it?
It is. So the Turing test is kind of this test for intelligence proposed by Alan Turing back in 1920s, 1930s, whereby if you have a person come into a room and he or she's interacting with a machine, or a person, but they do not know which. If the machine can fool the person into believing that they're interacting with a person, not a machine, then that is an indicative sign of intelligence. Now, it's quite weak in terms of its definition of intelligence, and it's moved on significantly since then. And there would have been a big program around the 50s or 60s. It was called the ELIZA program. Have any of you heard of that? It was basically your first chatbot. So what they found was they kind of came up with this kind of, again, it was just like, it understood the basic semantics of language. So you would say something like, you know, it was raining today, and it would ask you, did you bring an umbrella? It would have these associative rules. But again, very quickly, it would be shown to be not very intelligent and quite stupid. Okay. There's a very good documentary on one of the people who worked in that originally, and I have forgotten the name of it, but I will find it for you and I'll post it online because one of the original architects of that kind of went very against AI later in life. But it shows the history of it. It's a good documentary. Okay, so perform a complex surgical operation. What do you think?
I think there was some.
Yeah, I agree. In many ways, it's just a variant of our first example, even though we might want to think it, you know. So you'd have a robotic arm using computer vision with a few cameras to identify what it's looking for and be able to interact with it. Now, that will become more prevalent in the coming years, and you know what I mean, that bodes well for us all in terms of future healthcare. So, okay, what we're talking about tonight, we're going to talk about agents and environments, rationality, performance measure, environment, actuators and sensors, RPs, environment types and agent types. Okay, so first off, agents and environments. Now, a few definitions. So we have our agent, which is this guy, and it is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. The term percept refers to the agent's perceptual inputs at any given instant, okay? Important to remember that the percepts are at a particular instant. An agent's percept sequence is the complete history of everything the agent has ever perceived, okay? And typically, an agent's choice of action at any given instant can depend on the entire percept sequence observed up to that point in time, but not on anything it hasn't perceived, okay? So again, agents can include humans, robots, softbots, thermostats, etc. It really is just an abstract way of thinking about the world. If we want to take a mathematical view of it, we say that the agent's behavior is described by the agent function that maps any given percept sequence to a function. So again, here's our agent function, here's our percept sequence, and here's our mapping to an agent, okay? And this agent program runs in the physical architecture to produce F. So in many ways, we're concerned with driving this agent program to realize our agent function, okay? Does that make sense? Yes?
Yes.
Okay, so now that we have our agent function, if you could imagine tabulating the agent function that describes any given agent, so what would that require? That would require a table that contains all the percepts that the agent can see, as well as all the permutations of the percept sequence, okay? Now, very quickly, that will become a very large table for any world or environment you're modeling. It'll become infinite, unless we place a bound on the length of the percept sequences we want to consider, okay? So, we have to consider that when we're actually trying to identify a solution for realizing our agent function. And the table itself is an external characterization of the agent. Internally, the agent function for an artificial agent will be implemented by the agent program. So again, it's important to try and keep the idea of the agent function and the agent program distinct from each other, okay? The agent function is an abstract mathematical description, while the agent program is a concrete implementation running within some physical system. Okay, is that clear? Okay.
Yep.
So if we talk about now, we're going to consider a very basic world. It's the vacuum cleaner world. We have two locations, A and B. And the vacuum agent, which is this guy, perceives which square it is in and whether there's dirt in the square or not. It can choose to move left, move right, suck the dirt, or do nothing. So a very simple agent function is the following. If the current square is dirty, then suck it up. Otherwise, move to the other square. Now, a partial tabulation of this agent is shown here. Okay? So what do we see? We see our location and the state of that location. So A clean, A dirty, B clean, B dirty, A clean, A clean. So here we see a percept sequence where it's perceived that A is clean in two successive steps or time steps. Okay? And then we map that to our action. So we detect A is clean, we should move right. If we detect A is dirty, we should suck up the dirt, etc. Does that make sense? Now, we'd have to derive an agent program to realize this agent function. But we can define, a variety of vacuum-bound agents by changing the way we fill in our action column. Okay? So then the question is, what's the correct way to do this? So then, to answer what's the correct way to do this, we have to make a choice That choice is what makes the agent good or bad, intelligent or stupid. Okay? And typically, what we use for that is a performance measure, which will come in a while. Okay. So just kind
So
of to recap.
what about the input? Because I don't see like, okay, there is a percept and action, but sensors are getting the input. So in the agent function, there should be an input, right? So
On the agent function, there should be an input. Is that what you said?
yeah,
So like the agent function is the mathematical abstraction of the world, okay? So all we're doing is mapping these percepts and it can become infinite, you know? I'm not saying this is a real world agent. I'm not saying that we would grow to, you know, millions upon millions of percepts and specify these actions. That would be considered a poor agent in terms of performance, which we'll discuss in a little while. But in terms of mathematical abstraction, there's nothing wrong with specifying it in this manner, if that makes sense. You know what I'm saying? Like if we implemented an agent program that was meant to handle infinite percept sequences, when eventually we run out of memory and our entire program would crash and it would cease to function. Agreed?
okay, okay.
Yeah. So, okay, so in relation to our notion of agency, typically we're going to consider this as a tool for analyzing systems, not an absolute characterization that divides the world into agents and non-agents. Okay? And again, the reason for this is you can consider almost anything an agent. So again, the example they give in the reference text is a calculator. Consider 2 plus 2, the operation of that being an agent, where the actual action will be to provide 4 as a result. You know, but I mean, we don't understand anything more about the calculator by doing that, or the world in which it's operating. So that would be kind of a trivial example. Typically, in all areas of engineering, we can consider it as designing artifacts that interact with the world, and that we want to take a problem in the world, model it in a manner which we can perceive and act in an intelligent manner. Okay, and again, I suppose the perspective of Russell and Norvig, who are the kind of the authors of the reference text I use, basically AI operates at the most interesting end of the spectrum, where artifacts have significant computational resources and the task environment requires non-trivial decision making. So the whole non-trivial decision making warrants an intelligent action. Okay? So
how we can differentiate that, or maybe an example of non-agent?
oh, absolutely anything. You know, I mean, like in many ways, our little vacuum cleaning world, that wouldn't be considered a non-trivial example. Well, it would be in a 2-world tile. But imagine that world was of an arbitrary size. Okay? You defining an agent program that achieved your goal state of, say, cleaning a room would be a non-trivial task. And designing an agent program for that would be non-trivial. Like I would give the example of, do any of you have a Roomba or a robot vacuum cleaners in your house?
Yep.
No one? Yeah, lads. Okay, well, like, okay. So if you do, right, you know how they work. So I had a cheap one of the knockoff versions. Okay, and it was dumb. So all it did was you had your little charger location, and it walks randomly, changing, say, the degree at which it moves at a random locations. Now, the idea being that it will eventually cover the entire floor area, okay? And the only sensor it really had was where its home station was. so it will return to it when it was low on battery. Okay, everyone get that? Now, the challenge there is you're putting this device in a unseen or unexplored environment. Okay, so it's not even maintaining a model of the world. You know, it's not recording where it's going, so it can't backtrack to its original location, or it can't do it more efficiently. Now, if you splashed out and went for the Roomba, that does have additional sensors, so it can perceive more and it can actually identify its location. So what it can do is a much more efficient cleaning path. It can remember where obstacles in the room are. Okay, so each of these has the same goal. Okay, clean the room. This one had a better performance measure. Okay, but even mapping that out is a non-trivial exercise. Does that make sense? Okay.
Yep.
I assume
Yeah.
it does.
Yeah, thank you.
So like again, we'll explore these issues as time goes on, you know. But you know, like there are a variety of engineering challenges around which approach you take. You know, it's a cost trade-off for the manufacturer. It's a performance trade-off for the end user. The random one might warrant a larger battery because it takes longer to actually do the same workload. I mean, all these feed into both how we map out the agent function and how we realize that with our agent program. Okay. So, in the context of rationality, what is rational at any given time depends on four things. The performance measure, which we've already mentioned slightly, defines the criterion of success, the agent's prior knowledge of the environment, the actions the agent can perform, and the agent's percept sequence to date. To define a rational agent, for each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure given the evidence provided by the percept sequence or whatever built-in knowledge the agent has. Okay? Nothing really contentious there. But we could define those terms in a little more detail. So we need really to say what the performance measure is, what's known about the environment, and what the sensors and actuators, what they have. So if we make the following assumptions for our vacuum world example, let's say, okay? So our performance measure for this world and this agent is that it awards 1 point for each clean square at each time step over a lifetime of 1,000 time steps. So +1 for each time step at 1,000 TS. Okay, so this is kind of a generic way of evaluating how well it's doing. We assume that the geography of the environment is known beforehand, but the dirt distribution and the location of the agent is random. Okay, clean squares stay clean, and sucking action cleans the current square. Our left and right actions, so left to right, we have our actions, left to right, and we have suck. Moves the agent left to right, except when this would take the agent outside the environment. So if the agent is in A and it goes left, it just stays in A. The agent only perceives its location and whether the location contains dirt. So, okay. And under these circumstances, we can claim that this agent is rational and that its expected performance is at least as high as any other agents. Okay. So, does everyone agree with that? So again, like our basic premise is, if dirty, suck. If clean, move. So the agent will continually oscillate around the environment looking for dirt. Everyone get that?
Yeah.
Okay.
Yep.
So under what circumstances could we introduce irrationality to the agent? And I guess typically you're changing the performance measure to introduce, you're changing one of these to introduce irrationality, okay? So performance measure, for instance, would be an easy enough one. Well, we're saying plus 1 point for each time step at 1,000 time steps, okay? If we introduce a penalty for movement, okay, because that's consuming power, sorry, -1, then suddenly this agent will become irrational because it's hopping back and forth, you know, and its performance is going way down. So then how would we fix that? Or how would we make it rational again? We would introduce a measure that says once you have not seen dirt in X number of time steps, do nothing, okay? And in that case, we have recreated a rational agent or made it rational again. Does that make sense?
Yeah.
Now, if we were to change the environment, okay, and we were to say that over time, dirt randomly reappeared, then our no operation after X number of steps would suddenly again become irrational. So we would have to alter it again so that it would boot up at a whatever. It would statistically sample how often dirt reappears and do a search and hoovering for that time. Does that make sense?
Yeah.
Yeah.
Okay.
Yeah.
But again, there's other ways we can make this irrational in terms of like if we don't know the layout of the environment, okay, well we have to explore it rather than have it known in advance. You know, the agent could get stuck in a loop, for instance. You know, but we'll come across that later on. Okay. Okay. So, omniscience, learning, and autonomy. So, rationality is not the same as perfection. Rationality maximizes expected performance, while perfection maximizes actual performance. Okay. And when we think of perfection, you know, we kind of think of omniscience in that sense, and we have to kind of be careful to distinguish between the two. So, an omniscient agent would know the actual outcome of its actions, can act accordingly, so it knows what would happen. Okay, but this isn't always realistic or rational. And again, the example given was, you know, if you're crossing the road and it looks safe to cross, and something falls from the sky and crushes you, you know, I mean, you can't be held at fault for not knowing that that was going to happen. Okay, so if we then take a step back from this idea of perfection, because it's just a question of we have to be fair to the agents. The point is that we expect the agent to do what turns out to be the best action after the fact. It would be impossible to design an agent to fulfill perfection in that instance. Okay, so our definition of rationality, it doesn't require omniscience, because the rational choice depends only on the percept sequence to date. We also have to make sure that we haven't inadvertently allowed the agent to engage in unintelligent behavior. So, again, give the example of crossing the road. If an agent looks both ways to check for oncoming traffic, but the agent doesn't perceive that a truck is coming, that would be unintelligent behavior, considering you use both your actions and perceptions to check that. Okay. And then, okay, so assuming that we take care of both of them, does our definition of rationality say it's okay to cross the road? Not quite yet. It wouldn't be rational to cross the road given uninformative percept sequences. So the risk of crossing without checking would be too great. And secondly, a rational agent should choose the looking action before stepping onto the street, because looking helps maximize the expected performance. Okay. Now, so how do we achieve that? Typically, doing actions in order to modify future behaviors is referred to as information gathering. Okay. And it's an important part of rationality. Sorry. And the second part of that is exploration. Okay. And exploration is where it must be undertaken, say, by a vacuum cleaning agent in an initially unknown environment to try and understand its environment. Okay. And what can we do with this then? Ideally, we can learn, not only to gather information, but also to learn as much as possible from what it perceives. Okay. And ideally from that, what will arise is autonomy. So, whereby a rational agent should be autonomous, it should learn what it can to compensate for partial or incorrect prior knowledge. For example, a vacuum cleaning agent that learns to foresee where or when additional dirt will appear will do better than one that does not. And we'll see examples, primarily the reflex agent and the model-based agent, that address that question. Okay. Okay. So before we actually look at building agents or rational agents, we have to talk about the task environment, which are typically the problems to which the rational agent is a solution. So what we use to do that quite frequently is the piece description, so performance measure, environment, actuators, and sensors. To go through each of these in kind of sequence, performance measure. Okay, so like that's typically how you're saying you're doing a good job or a bad job. We already discussed it briefly. So they use the example of an autonomous taxi driver. So performance measure might be things like safe, is it fast, legal, did the customer enjoy the trip, was it profitable or not, wear and tear in the car, etc. The environment is again the model in which the agent has to act, so roads, traffic, pedestrians, etc. The actuators are the action the rational agent can take, so it can change the steering, accelerate, brake, signal other drivers, etc. Sensors, again, what would you assume? We have cameras, sonar, speedometer, GPS. Okay. All that makes sense. So, with regard to performance measure for our taxi driver, other desirable qualities would include getting to the correct destination while minimizing consumption of fuel, okay, and finding passengers, our clients, providing a good journey, earning tips, whatever you want. But what you'll find is that a lot of these measures will have conflicts, okay? And conflicts introduce trade-offs, okay? Can you give me an example of a trade-off in a performance measure for a taxi driver or an autonomous taxi driver?
Well, if you go too fast, it's no longer legal.
Yeah, exactly. So if you're going around the corner at 120,
Yeah,
it's neither legal, and your customer mightn't feel too safe either, But you get there faster, so you're achieving one metric.
yeah.
So you have to trade off these, okay? Again, in terms of the environment, so the taxi will have to deal with a variety of different environments. So if we're talking about rural roads or laneways with, hedges overgrowing and grass in the middle, to narrow city streets, you could have, motorways, dual carriageways. Again, all these different environments adds both additional percepts which have to be seen by our sensors and will require different actions to address. Okay. Again, like I know it's very varied because even different climates. So heavy rain, no rain, very hot, snow, ice, whatever. Okay. The actuators then are, again, as discussed, just the basic operations the human would have, and sensors, a variety of cameras. Okay. So it's self-explanatory, but I think it's kind of obvious that as both the number of sensors and actuators and the more varied the environment, the more complex the problem becomes, as well as the more criteria we have for a performance measure, the more complex the trade-offs will become in addressing. So, other examples to give, and again, it's good, lads, to get practice with viewing your worldview or model or environment you want to integrate with from this perspective. It really kind of focuses the mind on what you're trying to do. So, say for like medical diagnosis system, you could performance measure a healthy patient, reduce costs. What could be another performance measure for a diagnosis system?
Keeping health parameters in a certain range, in the healthy range, like blood pressure, like heart rates, sleep patterns, things like that.
Okay. Yeah, that will come under healthy patient in many ways. Like
response time, how quick to give you results.
Yeah. So response time or timeliness. Okay. They will be performance measures. And some things require. A checkup would have a much longer response time than, say, a cancer diagnosis or a COVID-19 diagnosis. We'll keep the times, okay? So the timeliness there will be a more significant performance measure, depending on the type of application you're going for. Similarly, your environment will differ, So if you're going for a hospital, whatever, patient staff, a GP surgery, a dentist, whatever you want,
So whether whether the performance can be measured based on the past history of the patient, like how like healthy he was, but like so based on that.
I mean, you're tracking, okay, but see, I guess it's kind of at present we're looking at this from the perspective of a single agent environment, okay.
Okay.
But when you're considering the patient's actions, say, it will become a multi-agent problem in some respects. Like I mean, what they're kind of getting at here is you have your patient, and they're pulling off your sensory input is like, we did a CAT scan or for the size of a tumor, and it's increasing or decreasing over time. Based as you have multiple scans. Mm-hmm. But if you were like, say, if you were kind of looking at the minutiae of the patient's health and like you're a GP surgery and you said, okay, take regular exercise and lay off high-fat food, you'd have to take into consideration the patient as a separate agent and entity in its own right. And that can become kind of a cooperative or a competitive agent in that sense, if that makes sense, because it's it's a third party's actions. Do you get what I'm saying?
Yeah, got it. Okay.
Okay. But then that's if we take example like say this guy, the parrot picking robot. Okay, so I mean it's just packing stuff away. But you could also add performance measures like it could be looking for defects in the part it's packing, etc. Okay. Okay. So now, task environments. We'll break it down into multiple different characteristics of these. Okay. And these are important because they describe our environment and the complexity of the environment. So if we're to say fully observable versus partially observable, if an agent sensors gives it access to the complete state of an environment at each point in time, then we say the task environment is fully observable. A task environment is effectively fully observable if the sensors detect all aspects that are relevant to the choice of action. Okay? Relevance typically depends on the performance measure. So where would an example be? Our vacuum cleaning world. If there's only one tile and the agent's in there, it's perceiving that the whole time. So that's effectively fully observable. Okay. So typically fully observable environments, they're convenient because the agent doesn't have to maintain any internal state to keep track of the state of the world. Okay, so it's just because everything's available to you, you don't have to model it. But an environment might be partially observable because of, say, noisy or inaccurate sensors, or because parts of the state are just missing from the sensor data. So again, take our vacuum cleaner example. If it only has a local dirt sensor, it cannot tell whether there's dirt in other squares, or the automated taxi that can't see what other drivers are thinking or how they'll act. If an agent has no sensors at all, then the environment is unobservable. Okay, and there are ways to work around that, which we may cover later in the course. So next, if we talk about single agent versus multi-agent, okay, so our distinction here is between single agent and multi-agent environments. It can seem simple enough, but it's not always very clear. So take the example of an agent that's solving a crossword by itself, okay? This is kind of a clear case, single agent environment. But an agent playing chess is a two-agent environment. But there are subtle issues between the two. So, and we first described how the entity may be viewed as an agent, but we've not explained which entities must be viewed as an agent. Okay, so explaining an entity as an agent as opposed to having to explain it as an agent. So if we go back to our taxi example, if the does the agent T1 for taxi 1 say have to treat another taxi T2 as an agent, or can it treat it as a physical object in the world that's acting to some physical rules, physical laws that we can model? Okay, so like in the same way it would react to, say, the weather. Okay, any thoughts?
You gotta treat it like an agent because it could do anything.
You do. And the reason you have to treat it as an agent is that T2's performance measure or behavior is best described as maximizing a performance measure whose value depends on T1. Okay? Because they're both competing in the same environment or cooperating in the same environment. They're both trying to get the same customers. Okay? So that's why you have to treat that as an agent, if that makes sense. Okay, if we take the example of chess, where the opponent is trying to maximize its performance measure against your agent, which by the rules of chess minimize your agent's performance. So that's why chess is a competitive multi-agent environment. Okay. Again, I already mentioned the taxi driving agent is the taxi driving is a competitive multi-agent environment, but it's also a cooperative multi-agent environment. Why so, do you think?
they're both trying to complete the same outcome. They're both trying to win the game.
Yeah, but again, so think about a performance measure. So safety was one of our criteria, wasn't it?
Yeah.
So me driving erratically puts you at danger, and you driving erratically puts me at danger. So we both cooperate to ensure we're achieving a safe destination or a safe aim, you know? So in that sense, we're cooperating while we're still competing, okay? I suppose the design agent problems in multi-agent environments, they're quite different from single agent. Typically, communication emerges as a property of rational behavior in multi-agent environments, while randomized behavior can also be considered rational in a multi-agent environment because it avoids pitfalls of predictability. Okay, so you can act unexpectedly. Okay, so deterministic versus stochastic. So if we say the next state of an environment is completely determined by the current state and the action executed by the agent, then we say the environment is deterministic. Okay, otherwise it's stochastic. So in this sense, an agent doesn't, when it's deterministic, an agent doesn't need to worry about uncertainty in a fully observable deterministic environment. Okay, because they're all it's a predetermined sequence of events in a world you can see and will inform with changes to the environment. So you don't have to worry about probabilities or potential events, etc. If the environment is partially observable, it can appear to be stochastic. Most real situations are typically so complex that it's impossible to keep track of changes practically. So we have to treat them as stochastic. Taxi driving, again, that's clearly stochastic because we can't predict the behavior of traffic exactly. In cause, we can't predict what will happen to the car, passenger, etc. The vacuum mode described, it is deterministic, but variations can include stochastic elements. Again, if we introduce the randomly appearing dirt or an unreliable suction hoover. Okay. We say an environment is uncertain if it's not fully observable or not deterministic. Okay. And like just in relation to our use of the word stochastic, it generally implies that uncertainty about outcomes is quantified in terms of probabilities, which we will get into later on when we're covering Bayesian networks. But in terms of a non-deterministic environment is one in which actions are characterized by their possible outcomes. So that refers to where there are, okay, so there are no probabilities associated with them because the agent must achieve the outcome state desired. It's only a question of which outcome, successful outcome it will arrive at. But we'll cover that again in more detail at a later stage. Okay, so episodic versus sequential. So episodic tasks, it's each of these are atomic episodes, so they have no bearing to our follow-on consequences. In each episode, the agent receives a percept, performs an action, but the next episode does not depend on the actions taken in the previous episodes. Loads of classification tasks are episodic. Again, if you go back to our example of the robot packing arm, if it's deciding if a product is defective or not, it doesn't base its decision on prior defective or non-defective products it's seen. Okay. In sequential, on the other hand, the current decision could affect all future decisions. So short-term actions can have long-term consequences. Again, chess and taxi driving are sequential in both cases. Now, naturally, episodic environments are much simpler than sequential environments because the agent does not need to think ahead. Okay? So, static versus dynamic. If the environment can change while an agent is deliberating, we say the environment is dynamic for the agent. Otherwise, it is static. Static environments are typically easy to deal with because the agent does not need to keep looking at the world while it is deciding on an action, nor does it have to worry about the passage of time. Dynamic environments, on the other hand, they're continually asking the agent what you want to do at that given instant. And if the agent hasn't decided, that counts as deciding to do nothing. Okay? If the environment itself doesn't change with the passage of time, but the agent's performance score does, then we say the environment is semi-dynamic. So again, in relation to our examples, taxi driving, that's clearly dynamic. Other cars in the track itself keep moving while driving, while the driving algorithm will figure out what to do next or where to go. Chess, when played with a clock, is semi-dynamic because you're being penalized for the time you're taking at making a move. And crossword puzzles are considered static. Okay. Discrete versus continuous. The discrete continuous distinction applies to the state of the environment, to the way time is handled, and to the percepts and actions of the agent. Again, we have an example of the chess environment has a finite number of distinct states if we exclude the clock. Chess also has a discrete set of percepts and actions. Taxi driving is a continuous state and continuous time problem. The speed and location of taxi and other vehicles go through a range of continuous values, so they're constantly changing. So the actions are also continuous. We're changing steering angle, movement directions. The input from the digital cameras is discrete, but it's typically treated as representing continuously varying intensities and locations. Okay. Then I have included known versus unknown. Okay, because this is typically a distinction that doesn't refer to the environment itself, but it refers to the agent designer's state of knowledge about the environment. So in a known environment, the outcomes or the probability associated with the outcomes, if it's stochastic, for the actions are known. If the environment is unknown, the agent will have to learn how it works in order to make good decisions. Okay. Note that, okay, so like the distinction between known and unknown environments isn't the same as that between fully and partially observable environments. It's possible for a known environment to be partially observable. The example we give is the game of patience or solitaire. You know the rules, but you're still unable to see the cards that have to be turned over. An unknown environment can be fully observable. So like again, a new video game, you can see the entire game stage, but you don't know what the buttons do until you try it. Okay, so what will be the hardest case, lads, from all these different characteristics of the task environment? So
Maybe dynamic cases could.
we'll start. We'll go in sequence. So fully or partially?
Partially.
Partially.
Single or multi?
Multi.
Multi.
Yeah. Deterministic or stochastic?
Stochastic.
Stochastic.
Episodic or sequential?
Sequential.
Sequential.
Static or dynamic?
Dynamic.
Yeah. Discrete or continuous?
Continuous.
Continuous.
And known or unknown?
Unknown.
Yeah, no.
Well done, lads. You got it in one. Fair juice to you. Okay.
Mars rover, maybe, right?
The wedge?
Would it?
Mars rover. The robots,
Yeah, yeah.
right?
Yeah, yeah. Okay. So let's take our examples of environments. So again,
So
here
I
are a
have-
few of the
Actually, one question I have in the previous slide, if you want to compare this like environment with the vacuum cleaner, so even the vacuum cleaner could be a dynamic, right? Because it doesn't know what sorts of obstructions it's going to face.
Well, the environment changes over time.
Okay, or whether it can be considered kind of a semi-dynamic because in the house we may not be keep moving the objects, right? So how that will be rated?
Well, okay. The dirt would be.
Mm-hmm.
Although it depends. So that would depend on. Let's say if your furniture isn't moving, and you're considering it static, okay. But no, dynamic. Dirt appears, okay, randomly around the house, right? So the only time that would change, no, it's a dynamic problem because
Okay,
you don't know what the dirt is. You have to find it each time.
got it.
Now, depending on your performance measure, I suppose. Okay. So, like, if you were to take the use case where you weren't rewarding the agent for cleaning the dirt.
Mm-hmm.
Okay.
Okay.
So if you had a agent that just purely the performance measure was, say, time. Okay.
Mm-hmm.
So then we could call it maybe semi-dynamic because the furniture is static.
Yeah, got it. Yes.
Getting penalized for the extra time it takes if you come across dirt, say.
Okay.
Because I just wanted the suction action or whatever, But again, you decide that by specifying your performance measure for that agent, okay?
Okay.
And your perceptions and your actuators have to align with that as well, okay?
Okay.
So, it's in your, it's totally in your power to make it what you want to be, as long as you follow the tenets presented.
Okay. Yeah. Yeah, got it. Thank you. Yeah.
Is there an added level of complexity that kind of can be brought about by what's supposedly fully observable environment that is actually partially observable? I'm just thinking of, let's say, you have a sensor in a raw material that's been transported around the world, and is a humidity sensor, and its ability to perform its function is impacted by humidity, say, but you don't necessarily, or dust, and you don't necessarily know that.
Yeah, that's a characteristic of its environment. Okay?
Yes.
So that's like the extremes of the environment it's operating in. So have you designed your sensor to accommodate that, or your agent, which is using that sensor to address that or not? Again, that's a question of the design, and that's up to you, or up to whoever's building it.
I suppose to paraphrase an infamous politician, it's kind of an unknown, isn't it?
But I mean, like, it's like they all have limitations. So, like,
yeah.
Let's say, and there's different ways of dealing with that. know? So, I mean, if your agent is actually, say it doesn't understand why it gets these values, but it's able to learn that there's a spike or a decline in values in certain periods.
Yes.
But it's not able to give a rationale for why the values are being derived. So over time, it could learn, if you were to do a learning agent, which we'll go on to later on, so it could prompt a response or a feedback, or it could alter its own results to address that issue. But again, typically, as the more generalizable, the more expressive the agent, the more complex it's going to be, and you're going to have to trade off between multiple facets of it.
Yeah, I'm just thinking of from the perspective of, like, everything else is pretty apparent if it's deterministic and stochastic or sequential. That's all pretty clear. Maybe the status of the agent being observable or partly, it can bring some complexity, maybe, but it's a good.
But again, okay, so we would define, so like if you were talking about humidity of a tank, whatever, okay, of a container,
yes,
we could say that's fully observable. We know the state of the tank at all times, okay? But if the extremes in the environment cause fault to that sensor, then we consider it a partially observable environment. You know, and we would treat it as such to address that failing. Okay, and then we'd have to put in place a strategy to get around that. You know, but yeah, look, we'll explore all that in a while. Okay, again, these are examples, lads, and just again, it's an example of how to specify the task environment and the different characteristics of it. Okay, and nothing there that's really too contentious. Okay, so again, I suppose, you know, our answers aren't always kind of like de facto. So like, you know, again, if we go back to the example of the part picking robot as episodic, okay, because it normally considers each part in isolation. But you know, if a large batch of defective parts come across, the robot should learn from several observations that the distribution of defects has changed, and it should modify the behavior. So similarly to what you're saying for your sensor on a container, you know. But look, we won't go through right now. But a lot of it does depend on the actual how the environment itself is defined. Okay, so if we talk about the structure of agents, so far we've talked about agents by describing behavior. The job of AI is to design an agent program that implements the agent function, the mapping from percepts to actions. We assume this program will run on some sort of computing device with physical sensors and actuators. We call this the architecture. So our agent equals our architecture of a program. And in general, the architecture makes the percepts from the sensors available to the program. It feeds the program's action choices to the actuators as they are generated. Does that make sense? We're extracting away two parts of it there. Okay. And then the appropriateness of the program chosen for the architecture has to be addressed. And we'll see different forms of realizing that architecture in a while. Okay. So agent programs. So agent skeleton, current percept as input from the sensors and return of action to the actuators. So this is like our base version of an agent, okay? We take in a percept, we respond with a action. Differentiate between the agent program, which takes the current percept as input, and the agent function, which takes the entire percept history. The agent program just takes the current percept as input because nothing more is available from the environment. If the agent's actions need to depend on the entire percept sequence, the agent will have to remember the percepts. So what we're seeing there, lads, is our agent percepts can only take in the current instance of the percept. If it's going to rely on historical data or previous observations, the agent is going to have to model the world at some capacity or persist that so we can actually pull back that information and act appropriately. So, a pseudocode agent. Table-driven agent takes in a percept, returns an action. What are we persisting? Percepts, a sequence initially empty. Table, a table of actions indexed by percept sequences initially fully specified. So, what are we saying there, lads? We're saying that, think back to our vacuum cleaner. So, our percept, run at day one, and we have whatever, a clean, okay, as our first percept. Now, this table is a permutation of all possible combinations of percept sequences for this agent for however many time steps it's required to run. Does that make sense?
Yeah.
Yeah.
So again, our sensor is giving us this percept. What we're doing is we're adding our percept to the end of our percepts, which is our sequence, which we're modeling. And then we're using a lookup action. So action, lookup, percepts table. So if we were to look up A clean from a percepts table, we would get move right, wouldn't we? And then our next percept would be taken in by the agent, which could be B dirty. So if our second guy then was B dirty. Okay? So what happens then is B dirty is added to the end of the percept sequence. So now we have A clean comma B dirty. And A clean comma B dirty is passed to the lookup table, and the action is returned, which in this case will be suck up the dirt. Okay? And then it would go again, and we'd have A clean, or we'd pass in B clean. And then B clean we passed on to the end of this percept sequence. And when A clean, B dirty, and B clean is passed to the lookup table, it would return move left, or whatever, depending on how defined the operation of the agent. Make sense? Okay. So
if the actuator, for example, there are some fault or something as unknown happen, in this case, how the program would react, right? There might be exception where it has to update the table or the percepts.
well, you see the table, okay. The percepts is what the agent is perceiving, okay? The table is separate. The table is like our lookup dictionary of mapping of potential sequences to an action, okay? So what you said there was if there was a fault. So let's take the example of, for the second step, if the dirt sensor didn't detect the dirt and it returned B clean by accident, okay? So we had A clean, B clean. That would be passed to the lookup table. So essentially the lookup table was saying, ask the table what we do when we have perceived a sequence of A clean, B clean. Now, because we have every possible permutation of sequences mapped to an action, then A clean, B clean would return probably move left. So then we'd have A clean, B clean, A clean. And then that would probably return move right. So we'd have A clean, B clean, A clean, B dirty, if the sensor got it right the second time. It was a one-off fault, okay? And then it would be cleaned. Does that make sense?
Yeah.
Okay. So a trivial agent program that keeps track of the percept sequence and then uses it to index into the table of actions. So okay, I explained that. The table vacuum world represents explicitly the agent function the agent program embodies. To build a rational agent in this way, we as designers must construct a table that contains the appropriate action for every possible percept sequence. Okay, that's fine. Now, why is the table-driven approach doomed to failure? Okay, if we say P is our set of all possible percepts, T is the lifetime of the agent, what will our lookup table look like? Well, we have the summation of P to the power of T for all values of T. Okay, so that gets pretty big pretty fast. Okay, if we consider our taxi example, okay, and they give this as an example of if we have a single camera which is giving us our percept input and it's taking in 27 megabytes, and that's a 30 frame per second, 640 by 480 pixel, 24 bits of color information. So for 1 hour of recording, that will give us, approximately, over 1 trillion entries in an hour, okay? Which is computationally infeasible to do anything with, okay? If we take chess as an example, which is, it's kind of well-defined rooms, you'd still have over 100,000, over 10,000 entries, sorry, about just over 10,000. So these tables become massive quickly. So no real no physical agent in the world will have the capacity to store the information required. Okay, it'll be one major issue we run into. Not for the chess agent now, but I mean, that was to show you the big tables. But for the taxi example, definitely. So either we can handle the physical capacity, either the designer won't have the time to create the table, because remember, it has to be fully specified before it's actually used, or no agent could ever learn all the right table entries from its experience. And even if its environment is simple enough to have a feasible table size, the designer still doesn't have much of a clue about filling the table entries, you know, in the correct manner. You know, like the example we gave a moment ago. Like, what if the sensor failed? You know, what's the appropriate action in that case? You know, when you're getting into percept sequences that contain thousands or hundreds of thousands or millions of actions. Okay. However, despite all this, the table-driven agent does what we want it to do for the vacuum cleaner world. It implements the desired agent function. The key challenge for AI is to find out how to write programs that, to the extent possible, produce rational behavior from a smallish program rather than a vast table. Okay, so that brings us on to basic agent programs. Okay, so we have simple reflex agents, model-based agents, goal-based agents, and utility-based agents. Each kind of agent program combines particular components in particular ways to generate actions. And they typically build on each other, lads. So it's kind of, it's following, one will follow on from the other to a certain extent. Okay. So for reflex agents, decision making is based only on the current. Okay, so these agents select action on the basis of the current percept, ignoring the rest of the percept history. So again, our example is the vacuum agent. So the basis of its decision making, for the vacuum cleaner world example, it's based only on the current location and on whether the location contains dirt or not. Okay. So let's have a look at the program. We're taking location and status, return an action. If status equals dirty, return suck, else if location equals B, then return right, else if location equals B, then return left. Okay. Now, this is a small program in comparison to the actual table we saw a while ago. The obvious reduction comes from ignoring our percept history. So we're cutting down the probabilities from 4 to the power to t, it's just 4. Okay. A small reduction again comes from the fact that when the current square is dirty, the action doesn't depend on location. If we were to embed this inside the conditions for location, we'd increase the number of things to consider. Okay, so simple reflex behaviors, they occur in more complex environments. Okay, again, if we think about our automated taxi, if the car in front brakes and the brake lights come on, you would want to notice that and brake yourself. Okay, so some processing is done on the visual input, and we come up with the condition: if the car in front is braking, then trigger the action, initiate braking. And what's that called, lads? A condition action rule. Okay, so you're all familiar with condition action rules, I assume. If you can do if else if, you pretty much have it. Yes? I hope so.
Yep.
Okay. So the limitations of this agent program, what are they, lads?
If it's not on the list, it's not happening.
Yeah. Well, like, it's stuck to this specific task environment, our two-world tile action. Anything else that are
It's not using any of its prior knowledge of the environment.
it doesn't have to, you know, and it's basic enough. Depending again, okay. It depends on the performance measure for that. But I mean, if we were to add a third tile, you know, then if we were to add a third tile and use this program, and let's just say that for the sake of argument they're all clean, What does the agent do? It goes right. It goes right. Now suddenly we're here. Dirt appears here, but we're never going to get back there with this agent program, are we? Well, it's A, B, so C, if that makes sense. Okay. So the schema and the program itself. So if we're building a general purpose interpreter for condition action rules, we create rules set for specific task environments. So our diagram over here has the structure of the general program in a schematic format. And we're showing how our condition action rules allow the agent to make the connection from the percept to the action. Okay, so the rectangles here, they denote the internal state of the agent's decision process, and the ovals represent the background information used in the process. Okay. The agent program is also pretty simple. Takes in a percept, it has a persistent set of rules, and it has a state which has interpret input percept. Okay. And this function generates an abstracted description of the current state from the percept. And the rule match function returns the first rule in the set of rules that matches the given state description. So the description in terms of rules and matching, it's purely conceptual. It can be implemented as anything, Boolean logic, whatever you want. Okay. So in this way, we're omitting our constraint of having to know the actual number of tiles in that world if we can make generic rules for navigating the world, okay? Which then would address the 3-tile world I mentioned a moment ago, okay?
So the condition action rules are static, or they are maybe, you know, a learning process where it will...
Typically they're static for reflex agents.
Yeah,
but,
okay.
But like you're trying to take away from, you're kind of trying to abstract away from your specific locations as much as you can, or anything that is specific. If you can abstract it and make it more generic, such that you can operate in a broader range of environments, that would be a good thing for a reflex agent. Does that make sense?
Clear.
Yeah. Okay. So, simple reflex agents have the admirable property of being simple, but they turn out to be of limited intelligence. The agent will only work if the correct decision can be made based on only the current percept. That is, only if the environment is fully observable. Okay. But do we have a workaround? So so a little bit of unobservability can cause big trouble for our agent. So again, if you go back to our braking example, so if the car in front brakes, then brake. You know, we're assuming that we can determine a brake light from a current percept. But if the car in front has a variation on what we consider a brake light to what we're used to, then our percept may not achieve that. So either we would brake continuously or we wouldn't brake at all. Either way, we wouldn't be able to manage that situation. Again, the same problem occurs in the vacuum world, where the simple reflex vacuum agent is deployed with its location sensor and only has a dirt sensor, because it can be dirty and clean, and it can suck in response to the dirt. So what does it do in response to clean? Like moving left would fail forever if it happens to start in the first square, and moving right would fail forever if it happens to start in square B. So like what's common for reflex agents is where infinite loops of failing behavior can occur. Now, there is a workaround to that. What is the workaround?
Like moving, not necessarily moving left or right, but just moving?
Yes, exactly. So randomization.
Yeah.
a randomized simple reflex agent might outperform a deterministic simple reflex agent. Okay? Because the random element makes it more generalizable to its environment. Again, take your the Roomba example. You know, it's dumb, but it's able to get there eventually by being random, and it's within a certain degree of angle. Okay, so that overcomes that limitation a little bit. Okay, but okay, I'll come to that later on. Okay, so the next guy, model-based reflex agents. So the most effective way to handle partial observability is for the agent to keep track of the part of the world it can't see now. So that is, the agent should maintain some sort of internal state that depends on the percept history and thereby reflects at least some of the unobserved aspects of the current state. Okay, so for our breaking problem, the internal state is not too extensive. Just the previous frame from the camera or so would do. It would allow the agent to detect when two red lights at the edge of the vehicle go on or off simultaneously. For other driving tasks, such as changing lanes, the agent would need to keep track of where other cars are, if you can't see them all at once. And for any driving to be possible, you know, it would have to have a good persistent model of the environment. And updating this internal state information as time goes by requires two kinds of knowledge to be encoded in the agent program. First, we need some information about how the world evolves, okay? So like the physical laws and properties, what happens over time? Is dirt randomly reappearing or not? Is, you know, how does speeding cars coming up in the inside lane of us affect our decision making, etc. Okay? And then we need our own actions and information on how they affect the world. Okay? So again, when we turn our steering wheel clockwise, we're going to go right. Okay? Etc. Like the knowledge about how the world works, whether implemented in either some Boolean format or a theory or a mathematical formula, is called a model of the world, okay? And any agent that uses that model is called a model-based agent, okay? Make sense?
Yep.
Yeah.
Okay. So again, we have our schema for this guy. Showing how the current percept is combined with the old internal state. So our percept's coming in through our sensors, and now we're actually looking at our state as well. We're saying how does the world change, what my actions will do, and taking all that information, we're deciding what action should I do now, and then we're looking at our condition action rules. Okay? So, and again, make that guy, model, rules. Okay. So we just added these two guys really to update it. We have to update the state of the world as well as our rule match and then return our action. Okay. So the update state is responsible for creating the new internal state description, and the details of how the models and states are represented can vary widely depending on the type of environment and technology used in the agent design. Okay, but like 2 seconds there, that's my window is leaking at me. There's a Felix in the ceiling, and when it rains, I get rain now. So, where are we at? Okay, so irrespective of kind of what representation we do use, it's not always possible for the agent to determine the current state of a, say, a partially observable environment. Exactly, you know. typically it's a best guess or approximation at the behest of the agent, you know. So again, you can take any example you want for our taxi. If there's a truck ahead of the taxi blocking its view of the lane next to it, it won't be able to see around the truck to know that what's there. Or if there's a hold up in traffic, it won't know what's causing that, you know. So there is uncertainty about the current state. It's unavoidable, but the agent still has to make a decision, and it's making a more informed decision, which should help. Okay. I suppose the less obvious point about kind of internal state maintained by a model-based agent is it doesn't have to describe what the world is like now in a literal sense. So like it's only in the context of what it's trying to do. So if the taxi is driving back home and there's a rule telling it to fill up on petrol, unless it has at least half a tank. Driving back home may seem to be an aspect of the world state, but the fact that the taxi destination is an aspect of the agent's internal state, not the world state. Okay. So again, like if you want to find it confusing, just consider that the agent could be in the exact same location at the same time, but have a different intent or destination in mind, you know, as a differentiator. Okay.
So the model could be coming from the memory of like a table that we have. So it can take into consideration previous, states.
So like the model is combining the agent's perceptions and its understanding of how the world evolves and its understanding of how its actions impact that world in deciding what it does. Okay? So again, like if you have your randomly appearing dirt, okay? Imagine your model is recording when it comes across a dirty tile and recording when each tile is dirty, you know? Can it inform itself as to how that world is changing or evolving over time? And thereby decide how many steps it takes to get to that tile to clean it. Does that make sense? In terms of maximizing its performance measure.
Right.
Okay. We'll explore it more as we go on, because like again, you know, it's kind of like, you know, the answer to your question will be part of the next kind of model almost, you know. So like the next one then lads is goal-based agent.
Yep.
So we know something about the current state of the environment, but it's not always enough to decide what to do. So the idea then is let's combine a goal with our model of the world. You know, now it's kind of an aim to reach for. Okay. So if we take an example, if we're at a road junction, we can turn left, turn right, and go straight on. The correct decision will depend on where the taxi is trying to get to. So, as well as a current state description, the goal agent needs some sort of goal information that describes situations that are desirable. So again, the typical example being arriving at the passenger's destination. Okay, but when we combine this goal with the model of the world, the agent program can combine this with the model, and the same information that was used in the model-based reflex agent can then be available to achieve the goal. Okay, so it can be straightforward and it can be not so straightforward. So like it's kind of when goal satisfaction results immediately from a single action, it's quite, you know, it's obvious. But it's more tricky when you have to consider long sequences of twists and turns in order to find a way to achieve the goal. That makes sense? So like, that really introduced concepts of search and planning, okay, which are like entire subfields of AI in their own right. Our next lecture will touch on search because we need to have a basic understanding of it to progress. But I mean, you could do a model on search in AI just in its own right, okay?
I have a general question on this, like different models. Okay, example, if you take a vacuum vacuum, so vacuum agent. So whether we need to use a single set of thing, example like goal based or like module based reflex for like implementation of the vacuum agent, or we can use a mix and merge.
I mean, like in many ways, the goal base is an extension of the model base, which is an extension of the reflex base. You know, they're kind of like they're built on top of each other in some respects. You know, now if you want to be strict about the differentiation of them, you'd have to align by that which defines them. So, like a reflex base couldn't maintain a state or maintain a model of the world in any way, or else would be considered a reflex-based agent. Similarly, a model-based agent couldn't have a goal, or would be considered a model-based.
Okay. Okay.
You know, but I mean, if your question is, are there situations where one outperforms the other? Then yes, absolutely. You know, depending on the situation. You know, I mean, we saw the example a while ago of the limited deterministic agent for the vacuum cleaning world, but that wasn't a model-based view. There are situations where one will outperform the other. Typically, it's in relation to computation. Okay, so like, your reflex is simple, but it requires no persistent history of the world. Your model does require persistent history. Your goal-based not only requires the model of the world, but also compute to search, how do I achieve my goal? You know?
Okay.
Does that make sense?
Yep, got it.
So again, okay, so this form of decision making, it's different from condition action rules, because we're now considering the future. You know, what will happen if I do such and such, or what will make me happy? You know, the reflex agent designs, the information wasn't explicitly represented because the built-in rules map directly from percepts to actions. So while the goal base can appear less efficient, it's more flexible because the knowledge that supports decisions is represented explicitly and it can be modified. Okay, so if it starts to rain, the agent can say, update its knowledge of how effectively it brakes, how its brakes will operate. You know, it'll take a longer time. And this causes all the subsequent behaviors to be altered to suit the new conditions we're experiencing. For the reflex agent, on the other hand, you'd have to rewrite bespoke condition action rules for each situation, and they quickly become so numerous that it's impossible to do. Okay? Okay, that makes sense? So we have the state, how the world evolves, what my actions do, what the world looks like now. Okay, and our future state is considered. Then we consider a goal, and then we decide what to do. Okay? Now, next guy. Utility-based agents. High quality behavior in most environments. Enter utility. So again, like goals alone aren't enough to get high performance or high quality behavior in most environments. You know, and there'll be lots of sequences that will get the taxi to the destination, thereby achieving the goal. But some are quicker and safer than others. Goals provide a kind of a distinction between are you happy or are you unhappy with the outcome. But a more generic performance measure would allow a comparison of the different world states that would allow us to quantify exactly how happy or unhappy we were with a particular result. Okay, and typically just use the word utility in place of happy. Okay, sorry. So the agent's utility function is an internalization of performance measure, you know, but it's not the only way to be rational. So we've already seen that the performance measure assigns a score to any given sequence of environment states. So it can easily distinguish between more and less desirable ways of getting to the taxi's destination. Utility function internalizes this process. Okay. So like an agent that chooses to maximize its utility would be considered rational according to the external performance measure, because it's getting the highest values for that. Okay. But again, this is not the only way to be rational. You know, we've already seen rational agents that have no idea what utility function is. You know, and in a couple of cases, goals are not fully adequate, but a utility-based agent can still make, I suppose, so in a couple of cases, a goal-based agent may be inadequate, but a utility-based agent can make rational decisions. You know, first when there's conflicting goals. Okay. Again, remember we have the trade-off between safety and speed. You know, the goal-based agent doesn't really have a way of handling that, but the utility function can specify the appropriate trade-offs of how important one is over the other. You know, and when there's several goals an agent can aim for, none of which can be achieved with certainty, utility provides a way in which the likelihood of success can be weighted against the importance of the goals. Okay, does that make sense?
So would it be right to say that utility provides you a way of prioritizing which goals, and if you can't achieve which ones?
What's the best worst outcome, or what's the, yeah, exactly. You know, so it's giving us a quantifiable number as to of the sequence of actions I have to take to arrive at my goal state, which is the best for me. Okay, and again it provides, if I have multiple goal states, how do I differentiate between the utility of them in terms of valuing one over the other, which helps the trade-off between them. Okay, make sense?
Yeah.
Okay, so partial observability and stochasticity are ubiquitous in the real world, and as a result, so is decision making under uncertainty. Now, a rational utility-based agent chooses the action that maximizes the expected utility of the action outcomes. So that's the utility the agent expects to derive on average, given the probability and utilities of each outcome. So the agent that possesses an explicit utility function can make rational decisions with a general purpose algorithm that does not depend on the specific utility function being maximized. So it's kind of like a global definition of rationality. Designating as rational the agent function that have the highest performance. And that in a sense turns into a local constraint, which can be expressed in a simple program. Okay? Now a definition of it? Okay. So again, it's what you'd expect to know. How happy I'm going to be in such a state being the major difference to evaluate my utility being passed into the action. But like, is that simple? We just build agents that maximize utility and job done. So like, okay, it's true that such agents are intelligent, but they're not simple. The utility agent has to model and keep track of the environment. That means it has to perceive its environment, it has to represent it accordingly, it has to reason about it, and it has to learn about the choice it's making. You know? So identifying the utility maximizing action is also difficult, and even algorithms typically with perfect rationality are usually unachievable, you know, because of the computational complexity associated with them. So, like, if you're utilizing your search approach, the search technique used for any complex setting won't guarantee the guaranteed highest utility solution, you know, which is why you use heuristic approaches to search to kind of get you a pretty good one, you know. But we'll talk about that more next week, okay? Okay, so last one, learning agent. So a learning agent can be divided into 4 conceptual components as depicted. We have the critic, the learning element, problem generator, and performance element. Okay. So to distinguish between them, between say the learning element, responsible for making improvements, and the performance element, responsible for selecting the actual external actions, this guy is typically considered what we've previously described as the entire agent. Takes in percepts, decides on actions. The learning agent takes feedback from the critic, and in doing so determines how the performance element should be modified to deal with it in the future. Okay. The design of the learning element depends very much on the design of the performance element. When trying to design an agent that learns a certain capability, the first question is typically not how am I going to get to learn this, but what kind of performance element will my agent need to do this once it has learned how. This is a very common approach in machine learning. Okay, typically if you're developing a model for machine learning, you specify the performance metrics for your evaluation of the model, and you focus on them so you have a collective understanding of are you making progress or not. Okay, so the critic then tells the learning element how well it's doing. Yeah, I mentioned that. Okay. So the last component, which we didn't mention, is the problem generator. Okay. So, and this is responsible for suggesting kind of actions that are off beaten track, you know. So it will lead to new experiences, and the rationale behind that is the performance element would keep doing on what gets the best results, but maybe there are better results if we look a little further afield, and so we should be willing to explore a little bit more, you know. So we're taking a suboptimal action in the short term to see what happens in the long term. Okay, and the problem generator's job is to select those actions. Okay, so that's all I'm going to say about the learning agent for now. Okay, but you know, typically, like all our agents, you know, they have a variety of components, and the components can be represented in many ways within the agent. So there's a great variety among the approach taken, but typically is a unifying theme in that, like, we want to modify each component to bring the components into close agreement with any feedback if we want to achieve learning in this context, okay? Thereby improving the overall performance. But we'll come back to this later on in a week's time. Okay, so this is just kind of a quick differentiation between the different components of how an agent program works. Now, we've described agent programs in high-level terms with various components where function is to answer questions: what is the world like? What action should I take? What do my actions do? The next question is, How do the components work? Now, there's basic distinctions among the various ways that the components can represent the environment the agent inhabits. Okay? And we can place the representations along an axis of increasing complexity and expressive power. And these are atomic, factored, and structured. Okay? To illustrate these ideas, it helps consider a particular agent component, such as the one that deals with what my actions do. So, atomic, each state of the world is indivisible. So no internal structure can be broken down. So if you consider the problem of finding a driving route from one end of the country to another via some sequence of cities. For the purpose of solving the problem, we can reduce the state of the world to just the name of the city we're in, a single atom of knowledge, okay? And that's the only discernible property for that, okay? And a number of algorithms use this approach in actually solving the problems. So like, you know, you're going from one city to the next city to the next city. And that's when you could conceptualize what the problem. So like search, game playing, hidden Markov models, Markov decision processes, they all work with atomic representations. And we'll cover all them as part of this course, okay? Or at least they treat the representations as if they were atomic. Now, if we move to the next higher fidelity representation, we're concerned with more than just one atomic location in one city or another. We might need to know more information about the problem. So petrol level, GPS locations, how the car is operating, etc. And this would be called a factor representation, okay? Where each state has a fixed set of variables or attributes, okay, as depicted there. While two atomic states have nothing in common, two different factored states can share common attributes, you know, such as GPS location or whatever, and not others, such as having petrol versus having no petrol, okay? You can also represent uncertainty. So if your petrol gauge is broken, you can be ignorant of the petrol, so you leave it blank, okay? And again, there are different subfields of AI that deal with these representations, typically constrained satisfaction problems, propositional logic, planning, and Bayesian networks, and machine learning algorithms. Okay, in this course, we don't look at constrained satisfaction problems in detail, nor do we look at machine learning in detail, but we will be looking at propositional logic, planning, and Bayesian networks. Okay? And the final guy is our structured representation. Okay? And like for the purpose of this, we need to understand the world as having things in it and that they're related to one another. Okay, not just variables with values. So again, an example that was given is if a large truck is ahead of us and it's reversing into a driveway, but a cow escapes from the farm and gets in the lane. Okay, then that results in like. It's highly unlikely that the representation used by that problem will prevent the truck from hitting the cow, unless it has a structural representation, which means it can take in the representation and identify the relation between the objects in an intuitive way. And again, things like relational databases, first-order logic, first-order probability models, knowledge-based learning, etc., NLP. They all cover that, okay? And they're focused on that. And we'll cover that in more detail, or some of them at least, in some ways. Now, lads, I think I'm out of time, am I? 7:58, okay. I know you've done a lecture at 8 o'clock, so it's okay for you to leave, and I'll finish up lecturing this, and it'll be in the recording, okay? Yeah, I have a reference text. I want to prepare kind of an overview video. Yeah, AI model approach, excellent book. My lecture was entirely based on the notes from that chapter 2, intelligent agents in that. It's excellent. It will prepare you for the whole MSc. I highly recommend getting it, but I'll give you that. I'll preach to you when I'm actually putting together the overview video, okay? So if you want to head off to your other lecture, that's fine. And
yeah.
I'll finish the recording and we'll finish up, okay?
So there is a fourth edition. Should we consider the fourth one of this AI modern approach, or third would be fine?
I'm working from the third edition because the fourth isn't available in Europe as of yet. You can import it from the US, but I'm working from the third, so that'd be fine. And it'd probably be a lot cheaper. Okay?
Right.
There are some digital copies in CIT library, to the best of my knowledge. I requested them last year. So go onto the CIT library, you might get an online edition. Okay?
Right. That will be our prime book, prime textbook, right?
Yeah. I'm telling you, it's like that book will serve you in every module you do as part of this MSc. You know, it'll give you a big understanding. So, like, I'd highly recommend getting it as reference text in general. I mean, I've used it for the last 10 years frequently. You know?
All right. Right.
So,
thank you.
Definitely get it. Okay.
Thank you.
Okay. Okay. That's all the best. Sorry. Okay.
Yeah, thank you.
Thank you.
Thanks a lot.
You.
Okay. So I'll finish up lecturing and then it'll be in the recording. Okay. So, like, what these different representations bring us, lads, is different degrees of expressiveness, and that's what we're really looking for. Okay. So the axes along which atomic, factored, and structural representations rise is the axis of increasing expressiveness. Okay. Now, typically, a more expressive representation can capture at least as concisely everything a less expensive one can capture, plus some more. Okay. So the more expressive language is much more concise. For example, the rules of chess can be written in a page or two of a structured representation, while they can take thousands of pages written in a factored representation. And this become very evident when we do first order propositional logic. Okay. However, on the other hand, the reasoning and learning become more complex as the expressive power of the representation increases. Okay. So to gain the experiences, to gain benefits of expressive representations while avoiding their drawbacks, intelligent systems in the real world may need to operate at all points along the axis simultaneously. Okay, that's chapter, I think it's in chapter 2 actually, I have to check it. I'm pretty sure it's chapter 2. Thanks for